General sessions, day 1. Man, do I have to use my classroom voice and all that? All right. So we've got the TBA talk, which turns out to be Jonathan Riehl, as the website indicates. And just another note, this 4:20 to 4:55 lightning talk scheduled in here is wrong. Go on back upstairs, and you'll find the talks after this talk. So, John works at Resilient Science, does amazing cloud work. I don't know anything about the cloud, but he does. So I'm going to turn it over and let him talk about his ROFL.
Thanks. So you also may have heard me mentioned in Numba. Been doing some work on that recently. But anyway, so TBA suddenly becomes this. So today I'm going to talk about a dialect of Python I've written called ROFL. Again, my name's John Riehl. I'm El Numero Uno at Resilient Science, and we do science on the cloud. But before I get into the details of stuff, I wanted to kind of do a higher level, start a higher level discussion, at least in your heads and in my mouth, about leveraging parallelism. So basically, the power densities are just not going to allow us to keep cranking up cycle speed. This is old news by now. I mean, this is like 5 years. This news is 5 years old at the latest. So what the architecture people have done is basically they've just increased the degree of parallelism available to us, and as developers, we kind of have to figure out how do we use that, and we have certain tools, but in some sense these tools are all kind of hodgepodge. So how do we as developers use parallelism? Well, we have some task parallelism, we have data parallelism. So for instance, we can use threads or we can use vector operations. NumPy is a great example of doing vector parallelism. We have tools for doing heterogeneous parallelism, where we have different kinds of cores, multiple, not just multiple cores, but different kinds of cores in the same platform. So we have things like OpenCL. And then over networks, how do we distribute our jobs across distributed resources? So we have a few answers for that as well. You have the grid engines, you have Hadoop, MapReduce type frameworks. And that's well and good for these particular domains. And what usually what I would assume happens is developers kind of pick a few of these things, and they get really good at them, and then they kind of live in that niche. But let's not forget the end user here. How can scientists and engineers use parallelism? Are we going to ask them to go out and learn OpenMP, for example, and how to mark up their for loops, which may be not necessarily something that they want to reason about too heavily. So at supercomputing last year, Michael McCool was talking about structured parallel programming. And I would kind of like to pitch as kind of a straw man here the idea of high-level structured parallel programming. So the essence of structured parallel programming is the creation of a set of patterns or basically data flow constructs that are readily nestable inside of each other. What you really kind of end up with in that world, though, is what I feel to be like a directed acyclic graph, if you're familiar with that, in terms of how data moves through a system and how we distribute that, how we could possibly distribute those computations. Moving to the more concrete, we have. I feel that we can leverage this. We can present this to end users at a higher level through using pulling in notions from functional programming. So we have a declarative semantics rather than an imperative semantics. We also eschew side effects, so that we can basically do things both at compile time, doing things like code motion, relatively easy, but also when we're distributing it, we can safely move code around, and whether it runs here or runs there, it doesn't matter. because that computation isn't side affecting anywhere else in the system. It's just taking an input and giving me an output. When I give it the same input, it gives me the same output every time. So another concept here, though, and I think this is really key to structured parallel programming, is the data-driven programming. So what we're doing here is we're replacing recursion with data traversal primitives. So we have these templates or patterns of data flow that we're nesting and building computations out of. And then finally, the high-level portion really comes from the traditional high-level programming canon. So we want to be able to present users with a simple, clean syntax. We don't want to have to declare our types, unless you're a power user. And we want to be able to we want to have at our disposal a set of really rich collection types. And that's where the resilient optimizing flow language, or ROFL, comes in. ROFL implements a lot of these features, and here I've kind of outlined how it does so. I borrow a lot of ideas from functional programming. Instead of using dynamic binding, I'm using let binding. That basically means that instead of, when I say A equals B, instead of assigning some value B that's computed for B to a memory space for A, or in the case of Python, having some sort of pointer in a dictionary pointing at the value for A. At compile time, I know that that's actually going to be a place in a stack, in a function call stack. And quite possibly it's something I can eliminate at compile time just by doing beta reduction. And so, as well, I'm also getting rid of the iteration primitive. So we're losing the for loop, we're losing the while loop. Although we're keeping the list comprehensions, and I don't think I actually give an example of that, but they're there. And then also we're making assumptions that if it's going to be something you want to, if you're expressing something in ROFL, your functions are going to be assumed to be a side effect free. That's not true at the moment, and I'm not 100% sure how to enforce that. Maybe some sort of evil type system at some point in the future. And so, but while we're taking away the while loops and the for loops, we're replacing it with well, first of all, vector operations. But also, we're presenting a set of data traversal primitives. And if you were sitting in the Copperhead talk this morning, we got to see a lot more of those than I'm actually going to get into. And then this is all built on top of Python. So I get the high-level programming, the high-level programmability of Python, and I get to pull in basically anything in the Python universe. I get to pull that into ROFL as well. So I get NumPy, I get SciPy, I could get Copperhead, I could get a wide variety of tools. It's all just Python at the end of the day. But it's Python with a set of high-level constraints that really make it easier to optimize and distribute. And we haven't seen the keynote tomorrow about superglue stuff, but I also feel that these kinds of directed acyclic graph languages present a good interface for defining workflow. And it's bound workflow. It's workflow that if I have an input, if I have a fixed input size, a fixed set of input, I know that the program is going to halt. So what we've just sort of gone through is the first bullet point in this, and what motivates ROFL. So and really, it's when I talk about parallelism and using parallelism. Of course, I went for the low-hanging fruit, and that's so we're going to see an example of embarrassing parallelism, and we want to give it to people in a way that they're not going to necessarily feel so guilty about doing it. But also, In my role as the CTO or chief scientist or whatever of resilient science, I'm meant to solve some business problems. So for instance, one of the nice things about this language that I'm not going to really talk to today is the safety. So because we're not allowing side effects, that reduces the likelihood, although it doesn't completely eliminate the likelihood of a very clever user coming into our system, writing code on our website, and then hacking our Amazon Web Services account. This bound and also bound iteration presents us the bound iteration and guaranteed termination give us another safety that we won't necessarily have runaway processes. Although I'm sure you could think of counterexamples where you're creating X range over Ackermann's function or something like that. Hopefully we can kind of look at the size of what that data would be, and we can say, well, you're going to have to go find another service provider. And then, but another thing, as an open source developer, I've been around the community for a while, and I really like SymPy. And SymPy, I think, makes a great intermediate representation, and hopefully I can get a little bit into that, although I don't really have time to go into the details. But for a long time now, I've been thinking, well, I haven't really fully implemented a functional programming language, and SymPy provides me with enough expressivity to do the untyped lambda calculus, and then I can play with these things that I've only heard about, like closure conversion or lambda lifting or things of that nature. So I got to do that in this project as well. So I've taken recursion away, and that makes the Fibonacci calculation is usually the first thing you whip out, at least in a language talk, when you want to say, here's my new language, look at how we do Fibonacci sequence in my language. What we're dealing with here is a function definition that just goes straight into an expression. And again, that expression syntax is just pure Python expression syntax. But there's a little problem there. We're using recursion in this example, and that's a no-no. So we're going to get back to this. But I just kind of wanted to page this in and maybe background a process for y'all to think about doing this in a data-driven language. So as a language implementer, I can't help but include a slide like this. I think pretty much every presentation I've ever given has had something like this, where I show the functional decomposition of my language implementation. ROFL is really a source-to-source translator that takes ROFL source code. It creates SymPy objects as an intermediate representation, and then it outputs Python source. So doing things of this nature is really easy for me, because I'm also the author of this project called Bazel, which is supposed to allow people the ability to easily extend or embed Python grammar into new languages. So spinning concrete syntax for domain-specific languages is supposed to be really easy in this project, but to my knowledge, I'm the only user of it. And then using SymPy as an intermediate representation is a real win here, because we get to do this let binding optimization where we get to basically take a value assignment and turn that into into lambda calculus, and then at compile time do beta reduction. So what that means is that basically every time it sees, if you say A equals B, every time it sees A in the code following, it just substitutes B into it. But then we also get to do SymPy gives us the ability to do common sub-expression elimination. So if B is appearing too many times in the code, it's going to recognize that as a common sub-expression and just lift it up into a single computation. So there's not going to be any redundant computation by inlining what's bound on the right-hand side of the expression. So I've kind of already gone into a little bit of the syntax and semantics. I find the ROFL makes the nut of for a simple, clean syntax. So I've basically taken all of Python's statement syntax and I've replaced it with these four productions, where basically a ROFL program is a series of definitions. And a definition is basically things of the nature A equals B or A equals expression. These can be lexically extended by using an optional where clause. And then basically what happens there is that what's inside the where clause is only bound inside the context of the right-hand side of the expression. And then you can also parameterize these things, so you create functions. This isn't entirely true to the semantics of the language, but I think as Python programmers, when you're writing ROFL code, it's really easy to kind of just think about it initially as the ROFL code shown here on the left-hand side just translates to the equivalent Python on the right-hand side. That's not entirely true, but that's a useful way of thinking about the semantics. And again, down here, that's just again more of this discussion about what a let binding expands into at the level of SymPy. And as I said earlier, what's going to happen here is that whenever SymPy sees an apply on a lambda expression, it's just going to go ahead and substitute any occurrence of the symbol x inside that ... with y. So if you're not tracking that, that's fine. That's the lambda calculus, and I don't. That was something that was kind of forced on me at the University of Chicago. But prior to that, I came from a strictly algol-based, as Dave McQueen puts it, C, C++, Python background. So you're gonna have to forgive the eye chart here. If I had had the time, and therefore TBA would have been me from the get-go, I probably would have had it shown a giant tensor or a multi-array of data points. And then we have a function that we're just going to want to apply to each point in that tensor. And then what that means is that our input tensor and our output tensor have the exact same shape. This is really kind of, to me, the essence of embarrassing parallelism. And numerical integration is a key example of an embarrassingly parallel application. So that's exactly what we're looking at here. We're looking at a piece of code that was originally due to a group at Stanford, and they originally implemented this in Igor Pro, and they kind of threw it over the wall to us to see if we couldn't get it to go faster. In about a day's time, I ported it to NumPy, and then with a few more minutes, I ported it to ROFL as well. And again, this is an eye chart, but I want to point out three things about this. First of all, we support nested functions, so you can see where we're nesting a function there. We do closures properly, so you can have names that reference things in the parent lexical scope. That's handled properly. We also support creating the closure for that, and so when it comes time to bind things, we already know what's what when we later on when we're using this Fermi func deriv. And then the second thing I wanted to point out is that we're really winning here at the parallel level, at the data parallel level, because of NumPy. I mean, this is whether this is ROFL or whether this is straight Python. These last three lines where we're changing this Z matrix, which we end up summing over. That used to be a too deep for loop, and now it's instead of being a for loop, it's just some lines of code. So we can do these kinds of things without the for loop or without the while loop, where we're assigning to Z sub I equals X sub I plus Y sub I. And I think I mentioned there was a third thing I wanted to point out here, and I lost it. All right, so to me, what I've been doing more recently is I've been thinking about this case where we aren't necessarily using embarrassingly parallel stuff. We want to have tensors, input tensors and output tensors, input multi-arrays, output multi-arrays of different shapes. And how we accomplish that is through a set of data traversal and mutation constructs. 1 minute? Okay, so anyway, this is Python's reduce basically, and this is how we do the Fibonacci sequence. So what we have to do is we have to synthesize some data here. That's being done by the X range. We create an accumulator where the first position in the accumulator is kind of the n-2, the second one is the n-1, and we index the result of reducing this adder that kind of tracks. So what we're doing here is we're threading state. We're kind of rethreading state, but instead of it being implicit state, it's now explicit state. Here's Mandelbrot. And so this approach has some risks and rewards here. We've seen a lot of talks today about languages that are basically Python or a subset of Python that use these functional constructs to get at data parallelism. So we're all kind of looking at the same jewel just through different facets. But I think we can all agree that this is going to require a higher degree of data literacy than we've seen at present. So we have some risks here. Do we need a Thinking in APL book? Again, I wanted to give some shout outs to SymPy. This was a lot of fun using it as an intermediate representation. A lot of the actual ideas behind ROFL were inherited from my former advisor's project Manticore, which is a semi-implicitly, semi-explicitly parallel superset of standard ML. And of course, the Python and scientific Python communities are absolutely necessary. Anyway, this is open source. We'll be using a BSD license, so you're more than welcome to grab it, play with it, and mutate it. Thanks.
Okay, I think we have time for one quick question, then we should all sprint upstairs to the lightning talks. Yeah, go ahead.
So I mean, you have that where clause thing, the way you're writing things, doesn't seem like Python to me.
No, it looks more like Haskell.
Right, so this isn't, I mean, you have one slide where you say it's just Python, and then it's not Python. So what exactly is the relationship?
When I say it's just Python, I'm trying to say, I know this looks a little bit weird, but relax, it's just Python.
Is that like, I mean, it just seems to me like the only thing it has is indentation.
No, it has lexical closure properties. So what that means is those names are only let bound in the context of the right-hand side of the parent definition. So similarly to the here, if I have this where and then a set of assignments, if I take that code and just block paste it into a function, that's going to have very similar semantics. And those whatever names I bind here are not going to be visible outside of this function. Similarly with the where clause.
The where is just Python, and the expression on the right-hand side is also just Python? Is that
So all the expression syntax is Python. The higher how we compose that is magic. Is not Python, right?
Okay, thank you. Okay.
Fantastic. Let's thank all the speakers in the session, and I think we're headed upstairs for the lightning talks, and then